Today we're going to talk about polygons a little bit, and you're going to find very quickly that this becomes an application of things that we learned earlier in Chapter 1, Section 3, using midpoint and distance formulas. So prepare to do a lot of practice in the coordinate plane and using our distance formula and stuff like that. Basically, the idea of a polygon, poly means many, gon is actually a word referring to angles. So the term polygon actually means many angles. And so a polygon is a shape that has 3 or more angles in it and is closed like this. Polygon is made up of sides. The sides are segments. And where 2 sides come together, we form a vertex. The number of sides is the same as the number of vertices. The plural of vertex is vertices. So that's an interesting little tidbit of information for you. So again, there's a very formal definition there of a polygon, but you've seen them before. Polygons can be triangles, quadrilaterals, pentagons, hexagons, septagons, octagons, whatever you want. Up 100 sides if you want. That's called a centagon. We'll talk more about names of polygons and things like that in the future, talk about their angles, talk about finding the areas of different polygons, all sorts of different things. That's a lot of what we do in geometry, is getting facts about polygons. Polygons can be convex or concave. How can we tell which one is concave? Well, concave has that word cave. It's like it's caved in. Which one of these, A or B, looks like a cave, like it's caved in? Obviously, concave goes with A. The opposite of concave is convex. That's convex. Another more formal way to define convex and concave is by talking about the diagonals of the polygon. And in a convex polygon, the diagonals are all inside the polygon. A diagonal connects 2 non-consecutive vertices. So there, I've got lots of diagonals in this thing. All sorts of diagonals. Look at all those diagonals. Every one of those diagonals is inside the polygon, isn't it? That's convex. In concave, some of the diagonals are outside of the actual polygon. So that's another way to define convex versus concave. But most people just remember concave looks like a cave. It's caved in. All right, so we're going to talk about perimeter and area. So immediately we're taking this geometric concept and we're going to put it in the coordinate plane and apply algebra to it. This is a pattern you're going to see a lot of. Find the perimeter of triangle ABC with vertices A at -2, 3. So let's get that first vertex. A is at -2, 3. B is at 3, -3. So that's right 3, down 3. And C is at -2, -3. Now, fortunately for us, when I connect the vertices with sides, I notice that 2 of my sides are perfectly horizontal or perfectly vertical. That means distance formula really isn't necessary for those 2 sides. Because a horizontal or vertical side, we can simply go ahead and count boxes to find the length. So AB is a little trickier, but AC is 1, 2, 3, 4, 5, 6 boxes long. And BC is 1, 2, 3, 4, 5 units long. To find the third side, we're going to have to use distance formula, or if you recall Pythagorean theorem, you could use that as well. We haven't learned that yet, so I'm not going to require Pythagorean theorem, but if you remember it, we could certainly use that because I know the other 2 sides, and clearly this is forming a right angle. So Pythagorean theorem applies. So this is kind of a special case, but use it if you got it. Let's go ahead and do it the other way, though. We would have to find AB using distance formula. So AB square root, we start our distance formula. We plug our coordinates in. The x coordinates are -2 and 3. The y coordinates are 3 and -3. So that -2 minus 3 is -5 squared. 3 minus -3 is the same as 3 plus 3, or 6 squared. Remember, -5 squared is positive 25. I can't square a number and get a negative in the real numbers. It doesn't work. Anytime I square it, I get a positive result. Unless you get some topics that you learn about in Algebra 2, then we're going to start fudging that a little bit down the road. 6 squared is 36, and so that's the square root of 51. So that third side, 61. Momentary lapse of brain power. And so my perimeter winds up being 6 plus 5 plus the square root of 61. And again, this is probably a place where we're probably going to decimally approximate that. Fortunately, today I did remember to bring a calculator with me. Hopefully it works. The 6 plus 5 is clearly 11, plus the square root of 61, plus square root of 61, and I get about 18.8. So the perimeter of that triangle is about 18.8 units, whatever those squares represent. Perimeter of this polygon, K, L, M, and N. So K is at -1, 1. There's K. Okay, L is at 4, 1. M is at 2, -2. And N is at -3, -2. Now, some people are saying, okay, that looks pretty easy, but how do I know which way to go around? I mean, do I start at K and then go to M, then to L? I mean, how do I connect these dots? And generally what you do is you connect them in the order they're given, going around. So we name and connect in order. So K to L, L to M, M to N, N to K. The shape appears to be some sort of parallelogram. Once again, I do have two perfectly horizontal sides. Those are going to be easy. So 1, 2, 3, 4, 5, and 1, 2, 4, 5. They're actually even congruent. So KL clearly is 5, and MN is also 5. The other thing you'll probably notice pretty quickly is that for both of these other two sides, I'm going down 3 and left 2, or right 2 and up 3. So those two other sides should be congruent as well. We'll let distance formula sort that out for us. So again, we're going to run two distance formulas. LM equals, and again, always indicate what it is you're measuring. Don't just write a distance formula down without indicating what it is you're measuring, because that's confusing to a reader. Someone looking at that doesn't necessarily notice right away what points you're using. They have to look back and reference the problem. Don't make them do that. Always indicate what it is you're measuring. The x-coordinates for L and M are 4 and 2. The y-coordinates are 1 and -2. So that's 4 minus 2 is 2 squared. 1 plus 2 is 3 squared. Notice my distances were 2 and 3, so 4 plus 9, or the square root of 13. And NK, setting up my distance formula, you're right, we probably are going to come up with the same thing, but we should still show our work. The coordinates are -3 and 1, and -2 and 1. So -3 minus 1 is I'm sorry, -3 and -1. Sorry, minus -1 there. That's much better. I was confused for a second. It wasn't working out. Watch that negative sign. -3 minus -1, -3 plus 1 is -2 squared plus -3 squared, or the square root of 4 plus 9, which is, again, the square root of 13. So it's 10 plus square root of 13 plus the square root of 13 for my perimeter. 10 plus, you could have said that's 10 plus 2 root 13 if you want to leave it exact. But again, we probably wouldn't do that. We probably 10 plus 2 root 13 in our calculator and get about 17.2. So applying distance formula, applying coordinate plane, looking for horizontal and vertical, that certainly helps me. Now, find the area of triangle DEF with these coordinates. The area this time and not the perimeter. Wait a minute, area? Area? We haven't talked about area yet. You're right, we haven't. But you learned about area of a triangle since you're in about 4th grade. So this shouldn't be a problem if we graph it. We know area is base times height divided by 2. So D is at 1, 3. E is at 4, -3. That's point E. And F is at -4, -3. So when I connect these points, and they're, oops, missed a little bit there. Let's try that again. Sorry. Arm's making a shadow on the smartboard, so it's a little bit difficult to see. There we go. So now I need to be able to figure out base and height and divide by 2. Now, any side of my triangle can be the base, and then we have to find the height to that other side. That could be really tricky, except I do have a horizontal side here. Okay, that's EF is my perfectly horizontal side. And that's easy to find that length because it's horizontal, 1, 2, 3, 4, 5, 6, 7, 8. That's 8 units long. So if I'm going to use that as my base, which makes the most sense because it's the easiest thing to do, the height has to be perpendicular to that and has to go to the vertex of the opposite side. So that has to be my height. Now that was not drawn in. We got to kind of draw that in ourselves, which again emphasizes the fact that a lot of times we need to be drawing the picture. We can't just go based on the numbers we see on the question. We actually have to draw the picture and interpret what's going on. Fortunately, the height is a vertical line. If this is a horizontal line, which again is easy to calculate, 1, 2, 3, 4, 5, 6 units. So the area is simply base times height divided by 2. Some of you learned this as 1/2 base height. It's the same thing. Doesn't matter. 6 times 8 is 48 divided by 2. Either way, we would 24 units squared is my area. We get the same answer either way. So again, what are we learning here? We have to read the problem. We have to know what it's asking. We have to be able to draw it and interpret it. So geometry asks a lot of us. This isn't just plug and go. This requires a lot of thought. Again, area of another polygon with a given vertices. This one, when we start plotting it, -3, 3. Okay. L is at 3, 3. M is at 3, -1. And N is at -3, -1. What do we got here? We got ourselves a rectangle. Couldn't be easier. 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4. 6 by 4 is 24 units squared. So don't panic if you see that. We're not going to give you super tough stuff at this point, but you are going to have to think a little bit in order to get stuff done. Application of that, very simple again, rectangle, count the squares, find the lengths of the sides, find the area. So that's what we got going today, working with coordinate plane and the idea of polygons in the coordinate plane.